Module 7, lecture number 2, we're going to talk about tests of joint hypotheses and why we would ever want to do a joint hypothesis test. So the motivation. Suppose we're curious whether school resources matter at all. For example, money spent on students and student class sizes have an effect on test scores. So let's let expenditures per pupil, EXPN, equal expenditures per pupil, and consider the population regression model. We have test scores as a function of student-teacher ratios. Test scores as a function of student-teacher ratios, the expenditures per pupil, and percent ESL. So the question we want to know is whether or not school resources matter at all. And we're defining school resources as these two things here, the expenditures per pupil and student-teacher ratio, or class sizes. So we're going to test a null hypothesis that school resources don't matter. In other words, beta 1 and beta 2 equal 0. And the alternative hypothesis that they do, which corresponds to the null hypothesis that beta 1 and beta 2 equal 0 versus the alternative hypothesis that beta 1 does not equal 0, beta 2 does not equal 0, or both. So note that this test of a joint hypothesis is one of these coefficients does not equal 0, then we reject our null hypothesis. And so we're testing against the null that both of them don't equal 0, and we're going to find out versus an alternative that one does not equal 0, or the other does not equal 0, or both do not equal 0. So a joint hypothesis, more formally, specifies values of two or more coefficients simultaneously. That is, it imposes restrictions on two or more coefficients. So a joint hypothesis will involve Q restrictions. In the example on the previous slide, Q was equal to 2, and the two restrictions were beta 1 equals 0 and beta 2 equals 0. We could test Q equals whatever we want, depending on the number of coefficients in the model. So if we have 10 variables in our model and there's 10 coefficients, well, we would have 11 because we would have an intercept. We could have 11 restrictions. So testing one coefficient at a time is not valid if we want to test both of them together. The resulting test will reject too often under the null hypothesis. The problem and the reason that this happens is that the coefficients are not independently distributed, and so their joint distribution is not normal. So we can't look up the values on the z-table if we're testing both coefficients simultaneously. If we're only concerned about one coefficient, like beta 1 or beta 2, then we can use our regular t-stats that we talked about in the previous lecture. But if we all of a sudden are concerned about two coefficients simultaneously, in this case beta 1 and beta 2, the problem is they're not independently distributed, and so we need a special test for that. Two solutions: we can use different critical values from 1.96, but it's difficult to know what the critical values would be because those critical values depend on the distributional assumptions. So we usually think of negative 1.96 as our critical value, but this depends on having a perfectly normal, a standard normal distribution curve, right? But we don't know what the joint distribution of the two coefficients are. And so we need some alternative methods for doing this. So we use different test statistics that test both beta 1 and beta 2 at once. The F statistic is the most common. So let's look at that. The F statistic tests all parts of joint hypotheses at once. The formula for a special case of a joint hypothesis, beta 1 equals beta 1 naught and beta 2 equals beta 2 naught in regression with two regressors, is F equals 1/2. So this is a two regressor case, or two restriction case, that we're going to take the t-stat of the first regressor and square it, plus the t-stat of the second regressor and square it, minus 2 times the correlation. So that p term, we call it rho, is the sample correlation. We know it's the sample because it has the little hat there. The sample correlation between the two t-stats times t1 and times t2. and then we're going to divide by 1 minus the correlation squared. And T1 and T2 are independent test statistics for beta 1 and beta 2. We learned about those in the previous lecture. We know how to calculate them. They're just, for example, T1 is going to be beta 1 hat minus beta 1 naught over the standard error of beta 1 hat. And the rule is reject the null when f is large. So how large, we'll talk about that in a moment. What makes f large? F large is when t1 or t2 is large. So if either of the variables has a coefficient that either variable x1 or x2 has a coefficient beta 1 or beta 2 that's highly statistically significant with a t-stat that's large, then we end up with an f-stat that's large, meaning we'll probably reject our null hypothesis. So this equation sort of gives us the reasoning why we can reject the joint hypothesis if either one of the coefficients is statistically significant, right? So if one is not, let's say beta 2 is not statistically significant, and the t-stat on beta 2 is equal to 0, then we can still reject our joint hypothesis if t1 is large enough. What's the large sample distribution of the F statistic? Why do we need to know this? Well, we need to know how to find critical values of the S statistic. And so we need to know what distribution we can look up values on. Consider the special case that T1 and T2 are independent, so the correlation between the two are equal to 0, is equal to 0. So when I say we're going to look up values of the F statistic, just like we know that the T statistic is normally distributed, meaning we can go to the Z table, we need to know what the distribution of the F statistic is so we can go look it up on a particular table. So if we assume that the two are independent, T1 and T2, then the correlation trends to 0, and so in large samples the formula becomes approximately 1/2 times T1 squared plus T2 squared. So what does this look like? This is just a sample average, right? We have two values, T1 and T2, and dividing by 2. Well, it's a sample average of the squared terms. Under the null, T1 and T2 have standard normal distributions. We know that in this, and in the special case, they're independent. So what do we mean by that? We mean T1 is normally distributed with mean 0 and variance 1. In large sample, the large sample distribution of an f-stat is the distribution of the average of two independently distributed squared standard normal random variables. That's just what we're describing here. So, or that's just what we've written here. We have two independently distributed squared standard normal random variables. And so we know what that distribution is. Luckily, we know that. It's a chi-squared distribution with q degrees of freedom. And we write chi-squared is just this little kind of fancy x thing here. The squared part is this little squared term here. And the number of degrees of freedom is going to be q. And it's defined as defined to be the distribution of the sum of q independent squared standard normal random variables. That's exactly what we were talking about in the previous slide. The two t-stat squared divided by 2. In large samples, the F distribution the F distribution is written as chi-squared q divided by q, where q is the number of degrees of freedom. And so here are some selected large sample critical values of chi-squared divided by q. And these are going to be just like our t-stat rejection rule. We're now defining the f-stat rejection rules. So let's say we have one degree of freedom. We're testing one hypothesis. Our 5% critical value or 95% confidence rejection rule would be reject the f-stat. Reject the f-stat if f-stat is greater than 3.84. So f-stat with 1 degree of freedom, we reject with 95% confidence if it's greater than 3.84. If we have 2 degrees of freedom, so we're testing two coefficients simultaneously, then we reject if the f-stat is greater than 3. If we test 3 coefficients, then we would reject if the f-stat's greater than 2.6. 4 coefficients we would reject if the coefficient's greater than, or if the f-stat's greater than 2.37, and so on. And so you can look up these values on a chi-squared table in the back of the book or online. Alright, so we talked in the beginning about how this is related to model fit when we talked about school resources mattering or not. Let's make this a little more formal, and suppose you have a model where you're regressing yi on x1, x2, and x3. You're primarily interested in the relationship between x1 and y, and so you want to get an unbiased estimate of beta 1. We said that perhaps just estimating a single model, single regressor model, let's say that our single regressor model looks like this. We know that this one might suffer from omitted variable bias because x2 and x3 are contained in the error term here in ui. And so we want to test which one's a better model, 1 or 2, the multiple regressor model. We can do this by testing simultaneously the joint hypothesis that beta 2 and beta 3 are equal to 0. So our hypothesis is that beta 2 equals beta 3 equals 0. We're jointly testing x2 and x3, whether x2 and x3 have no effect on y. So what the f-stat does for us is it says if the f-stat on the first model, well actually this would be the second model in this case, is large, this suggests that we can strongly reject the null hypothesis that x2 and x3 don't matter, meaning that model 2 is a better model than model 1. If we fail to reject this null hypothesis, this means that x2 and x3 don't matter, and so maybe model 1 is a better model. But really we're still in the land of argument. We need to make the argument that ui is uncorrelated with xi. And this is just one method for helping us make that argument.